Today, the topic of discussion is on centroid and center of gravity of engineering mechanics, module 4, part 2, ESME 301. It is Papa's theorem. This theorem deal with surfaces and bodies of revolution. A surface of revolution is defined as a surface which may be generated by rotating a plane curve about a fixed axis. From theorem 1, that is, the area of the surface generated by rotating any plane curve about a non-intersecting axis in its plane is equal to the product of the length of the curve and the distance travelled by its centroid. Now, for example, a surface of a cone may be obtained by rotating a straight line AB about axis AA dash. The surface of a sphere, similarly from the figure 2, the surface of a sphere by rotating a semicircular arc ABC about its diametral axis AC. Now, from the figure 3, that is, consider AB is any plane curve of length L lies in XY plane and does not intersect the x-axis. Let the length of the curve AB, that is, AB is divided into large number of small elements. Let y coordinate of the midpoint of any element, that is del Li, is denoted by y bar, and that of the centroid C of the entire curve AB by y bar. Now let the plane of the curve is rotated through any angle alpha measured in radian about y-axis. The distance travelled by the midpoint of an element, that is del Li, is alpha yi, and the area of the curve surface generated by this ith element is del Li alpha yi. Hence, the area of the surface generated by whole curve AB becomes summation of del Li alpha yi, that is alpha summation of del Li yi alpha y bar L, where L is the angle of rotation of the curve measured in radians about the x-axis. Now, Papa's theorem 2. The volume of the solid generated by rotating any plane figure about a non-intersecting axis in its plane is equal to the product of the area of the figure and the distance travelled by its centroid. In this diagram, in this figure 4, a body of revolution is defined, a body which may be generated by rotating any plane area about a fixed axis. A solid cone may be obtained by rotating a triangular area. Similarly, a sphere by rotating a semicircular area, that is shown in figure 5. Now, in the figure 6, that is, they consider any plane figure of area A and is divided into large number of very thin strips parallel to x-axis. Let y coordinate of the middle of the strip of area, that is del AI, is yi, and now let the plane of the figure is rotated through any angle alpha about x-axis. So any element of an area del AI generates a sector of a thin ring of volume equal to del AI alpha yi. Hence, the total volume generated by the whole figure, that is summation of del AI alpha yi, that is alpha summation of del AI yi alpha y bar A, where alpha is the angle of rotation of the figure measured in radian about x-axis. Now, problem number 1. Determine the coordinate x bar and y bar of the centroid C of the area of the quadrant of an ellipse OAB with major and minor semi-axis A and B respectively as shown in the figure 7. Consider an elemental strip of height y and width dx parallel to y-axis at a distance x from y-axis. Now, the area of the elemental strip, that is dA, that is nothing but y into dx. So, its moment of area AB about its x-axis, so that is y by 2 into dA. So, putting the value of dA, so finally y square by 2 into dx. Now, moment of total area about x-axis, that is integration 0 to a y square by 2 into dx. That is equation number 1. The equation of an ellipse is nothing but x square by a square plus y square by b square equals to 1. So, from this y square equals to b square by a square into a square minus x square. So, this is equation number 2. Putting the value of y square in equation 1, we get, that is moment of total area about x-axis, that is nothing but half of integration 0 to a b square by a square into a square minus x square dx. So, we have to integrate it first, and finally we will get the that is ab square by 3. Now, the total area of the quadrant of an ellipse, that is OAB, is given by a equals to nothing but the integration of this, putting the limit 0 to a, finally a equals to pi AB by 4. Now, the distance of the centroid C from the x-axis, that is y bar equals to integration y dA by a, that means the total moment of area by total area, putting the value of y dA and also a, we will get the value of y bar, that is 4b by 3 pi. Similarly x bar should be integration x dA by a. So, putting the value of x, putting the value of dA and the limit, we will get the value of x bar, that is 4a by 3 pi. So, the coordinate of C of the given area, that is x bar is 4a by 3 pi and y bar equals to 4b by 3 pi. Now, problem number 2. So, problem number 2, that is referring to the figure 8, proof that if the equation of a curve OA referred to the coordinate axis x and y taken along two adjacent sides of a rectangle ODAB is y equals to kx to the power m, then the coordinate x bar and y bar of the centroid C of an area of the shaded spandrel OAB is given by, that is x equals to m plus 1 by m plus 2 into a and y bar equals to m plus 1 by 4m plus 2 into b. Now, consider an elemental strip just like the previous problem of the width dx and height y. So, the area of the elemental strip is nothing but dA equals to y into dx. Now, the coordinate of centroid of the area, that is dA equals to x comma y by 2. Now we have to calculate the x bar. So x bar is nothing but integration x dA by integration dA. So putting the value of dA and putting the value of limit 0 to a. So finally, just by integration, finally we will get the value of x bar, that is m plus 1 by m plus 2 into a. Now the point A lies on the curve OA, so hence A equals to that is A, point A, that is AB, being a point on the curve, so it will satisfy the equation. So value of B equals to k into a to the power m and k equals to b by a to the power m. The equation of the curve OA, that is y equals to kx to the power m. So finally y equals to b by a to the power m x to the power m. Now again y bar equals to, we know that moment of area by total area. So y by 2 into dA and putting the value of dA and the limit should be 0 to a and finally just by indication we will get the value of y bar. It is nothing but m plus 1 by 4m plus 2 into b. Now the centroid of the coordinate of the centroid of the shaded area is given by x bar equals to m plus 1 by m plus 2 into a, and y bar equals to m plus 1 by 4m plus 2 into b. Now problem number 3, that is using the second moment of second theorem of Pappus, calculate the volume of the ring shown in this figure 8, where capital R equals to 25 centimeter and small r equals to 10 centimeter. Now divide the figure as shown in it is indicated by part A and part 1, part 2 and part 3. The coordinate of the centroid part 1, 2 and 3 with respect to OO axis are x1 equals to r minus 4r by 3 pi and x2 equals to x3, that is r plus 4r by 3 pi. So this figure is symmetry about the vertical axis. So the centroid lying on the x-axis. So we have to calculate only the x bar. Now the area of the each part, that is a1 equals to a2 equals to a3, is nothing but pi r square by 4. So summation, x bar equals to summation of xi ai by summation of ai. So putting the value of all the values, and we will get the value of x bar, that is 1/3 3r plus 4r by 3 pi. Now from the second theorem of Pappus, we know that the volume equals to the distance covered by the centroid of an revolution into area. So the distance covered by the centroid of the one revolution, that is 2 pi 1/3 4r 3r plus 4r by 3 pi, and the area equals to 3 by 4 pi r square. So putting the value of capital R and small r, we will get the finally, that is volume equals to 39105 centimeter cube. Okay, thank you very much.